Okay, as we continue on our magical tour of circles, everything circles this unit, we'll be taking a look at chords and how chords cut circles up into different arcs. So can we use chords and circles to find lengths and arc measures? Of course, a chord will always cut a circle into two pieces, two different arcs. And if the chord happens to be the diameter, right, the chord goes through the center of the circle, well, then the arcs will actually be equal in measurement, right, because they'll be congruent. They'll each be a semicircle. So that's maybe not quite so exciting. What's more exciting is when the chord is not a diameter. Because if the chord is not a diameter, then the arcs will not be congruent. One of them will be larger than the other. So we'll have a major arc, which will have a larger measurement than the minor arc, right? The major arc will have a measurement greater than 180 degrees. The minor arc will have a measurement less than 180 degrees. Well, gotta talk about being congruent again. So just like before when we said that the minor arcs would be congruent if the central angles were congruent, same thing here. The minor arcs must be congruent if those chords are congruent. Right? The arcs are congruent if and only if the chords are congruent. Previous lesson, it was the central angles that had to be congruent. Well, we're not working with central angles this lesson. We're working with chords. Hey, perpendicular, let's throw 90 degrees in the picture and see what happens. All right, so we've got a chord and a diameter, right? So we've got two different line segments here. We've got a chord, got a diameter. If the diameter bisects the chord, we know it's perpendicular. Right? So if EG is a diameter and EG happens to be perpendicular to DF, segment DF has been bisected. So we know each half is equal in length or they're congruent. Right? So HD has to be congruent to segment HF. And then the arcs have to be congruent. So arc GD will be congruent to arc GF. And so going the opposite direction, right? If I know they bisect, if the diameter bisects the chord, and say, hey, that first one had to be a diameter. Right? If segment QS is a perpendicular bisector of segment TR, then I know segment QS, not only is it a chord, it happens to be the diameter. Notice it's not just bisecting and not just being perpendicular, it's got to be both. One of the chords has to be bisected, and that intersection has to be a 90-degree intersection. Two chords will be congruent if and only if they're the same distance from the center, right? That's what equidistant means. Remember, if we want to try finding the distance from a line segment to a point, we also wanted to go in a perpendicular direction. So I know segment AB is congruent to segment CD if and only if distance EF equals distance EG. Again, perpendicular is a key thing here. If I did not know that those were 90-degree angles, I could not conclude anything. Okay, that was a whole bunch of different theorems and everything else under the sun, so let's actually try to use some numbers. You might notice that my equation editor does some silly things sometimes with those arc symbols. My apologies, but after banging my head against the wall for enough time, I decided I'd just let this one go the way it goes. Microsoft's equation editor is just not real friendly with that arc symbol. So, we know the measurement of arc AB is 110 degrees. We want to find the measure of arc BC, the measure of arc ABC, and the measure of arc AC. Well, where to begin? Well, segment AB is congruent to segment BC, right? Because they both have a length of 9, so they got to be congruent. So I know those arcs have to be congruent. I know arc AB has to be congruent to arc BC. So I know the measure of arc BC has to be 110 degrees because the measure of arc AB was 110. Well, how about the measure of arc ABC? Well, I know I can just add the measurement of those arcs together because those arcs intersect at exactly one point, point B. So the measure of arc AB plus the measure of arc BC will add up to the measure of arc ABC. So I know 110 degrees plus 110 degrees is 220 degrees. How about the measure of arc AC? Well, I know the entire circle is 360 degrees. So I know the measure of arc AC plus the measure of arc ABC has to be 360 degrees. I just figured out the measure of the measure of arc ABC is 220 degrees. So just a little bit of arithmetic and I can figure out, hey, 140 degrees will be the measurement of arc AC. Okay. We want to find the distance from C to E. We want to find the measurement of arc CE. We want to find the measurement of arc BC. Well, we have a diameter. We have a perpendicular intersection. Because BD is a diameter, and because it's perpendicular to segment CE, we know segment CE has been bisected. So if the distance from C to F is 5, the distance from F to E also has to be 5. So the distance from C to E will have to be 5 plus 5, which is 10. And of course, we know that since segment CF is congruent to segment EF, we know those arcs must be congruent. arc CD must be congruent to arc DE. And so their measurements have to be equal, right? If the arcs are congruent, the measurements are equal. So 9x has to be equal to 80 minus x. And again, even though the name of this class is called geometry, notice how much algebra we have to do. I can add x to each side. I can divide by 10. And I come up with 8. Of course, the question wasn't find x. The question is, can you find the measurement of arc CE? Well, I know the measurement of arc CD is 9x degrees. So 9 times 8 degrees is 72 degrees. Of course, I know the measure of arc DE is 80 minus x degrees. So that becomes 80 minus 8 degrees, which is 72 degrees. Or I could have used the fact that those two arcs have to be congruent, so therefore I knew that if one of them measures 72 degrees, the other also must measure 72 degrees. But this is a nice way of confirming that x really is 8, because when I plug 8 into each expression, it comes out to be the same value, 72 degrees. So, of course, the measure of arc CE will be 72 plus 72, which is 144. So the measure of arc CE is 144 degrees. Oh, but we also need the measure of arc BC. Well, we've got a diameter in play, right? Segment BD is a diameter because it's a chord that happens to go through the center of the circle. So we're looking at a semicircle, and I know that the measure of the arc BC plus the measure of the arc CD has to be 180 degrees. But we just found out a moment ago that the measure of arc CD is 72 degrees. So a little bit of computation. Measure of arc BC has to be 108 degrees. Because 108 plus 72 makes 180. Whoa, there's a bunch going on in this diagram. We've got a diameter, right? Segment WX is a diameter. I've got a chord Q, segment QR, another chord in segment ST. Notice they've drawn in a nice little radius, segment QC, that's a radius. Notice the segment that just goes from C to U has a length of 2x. And then it looks like the length of the segment from C to V is 5x minus 9. So what on earth are we going to do here? We're trying to figure out the radius of circle C. Okay. Segment QR and segment ST are congruent chords. Right up in the directions it says, hey, they're equal to each other in length and they both have length 16. We know that segment QR and segment ST have to be the same distance from C. So I know CU has to equal CV. Oh, that's the equation we can set up now. CU has to equal CV. This will enable us to find the value of x. Right, obviously a couple steps got done there. X is 3. So the distance of CU is going to be 2 times x, which is 2 times 3, which is 6. Now, because we have a diameter intersecting a chord and it's perpendicular, we know that to be bisected. So the distance from Q to U is half of that chord. Since the whole chord was 16, we know half of 16 is 8. So now we have two sides of a right triangle. We've got the legs. Right? The distance from C to U was 6. The distance from Q to U was 8. Those are legs of a right triangle. The hypotenuse of the right triangle is the radius of that circle. Pythagorean theorem can quickly tell me that the distance from Q to C is 10. Therefore, the radius of circle C is 10 units. Before I turn you loose for the IXL, we've talked about a radius. We've talked about the center of a circle. We've talked about a diameter. We've talked about central angles. We've not talked about sectors, and the IXL I want you to work on today. There's a lot of multiple choice questions, and one of the things they want you to identify is a sector. So that's what a sector looks like. You got the central angle, you've got the arc that goes with the central angle, and then that whole area that's shaded in, that's a sector. All right. I think all the rest of the vocabulary that's going to show up in the IXL we've covered. You know what a radius looks like, you know what the center of the circle looks like, you know what a central angle looks like. The sector is the one thing we've not done. Right? That's actually an area of the interior of the circle. So again, worksheet we can work on. Make sure you understand what you're doing. Don't just race to get done. And then, of course, the IXL will be identifying parts of a circle.